All right, I think we should probably get started again, especially since I've got a long talk. So I'm worried about sticking to time as well. Same deal as before. So if you've got questions, ask questions. If I need to, I'll chop some stuff out at the end of the talk to stay on time. But it's a learning experience. I've stuck the whiteboard up in case we need the whiteboard, and we have one marker pen, which is not permanent. So we actually have one pen. It should last the day. We'll see how much you ask. All right. So what I want to talk about today is control. So equivariant systems has only really recently being used in control, right? So invariant systems and geometric control is a really well-established field. So, you know, from the 80s with Jesse Grizzle's work and Brockett and Sastry and all of these dudes. And then it went into Marsden and Abraham, Ratui and Bloch and all of these people that did the invariants and the reductions and the mechanical connections and all of that sort of work. So that field is historically really well established. But equivariance is different, right? So invariance typically tackles a free group action that is non-transitive on the space, and it studies dynamical systems for which that group action is an invariant. So usually the Hamiltonian is invariant to that action. So you'll have a kinetic energy, you apply the invariance, you don't change the Hamiltonian, and then you get all this model reduction stuff that you can do. So it's a free group action, it's non-transitive, geometric control. So what we're doing here with equivariance is a transitive group action that's often not free, okay? And we don't do invariance because the invariance isn't there for a transitive group action. What we do is we use the group to coordinatize the control problem. And it's exactly, we look for a system, we find a lifted system on the group, and we re-express some of the problems on the group, and then we work through what's going on. So the point is that the control problem wasn't where we started, right? We started with the observer problem because that's the one that we actually were tackling at the time. And there's sort of a question mark about, well, how do you go about taking some of these tools and doing control? And we don't want to replicate geometric control. All right, so let me just run quickly through what we're trying to do. So we're looking at some of these problems, like, you know, physical systems, like these two planes. And take off. I'll just start the little demo at the same time. So this is, I work a lot with Andrew Tridgell and ArchiPilot, as most of you know. And what we're actually doing here is coordinated acrobatics. So we have the two little planes. We have an idea of the trajectory that we're trying to follow. So this is a pre-specified trajectory. And the goal here is to make the plane fly along the pre-specified trajectory, okay, subject to all the wind and everything. And this is additionally a coordinated problem. So we're actually trying to get the planes, they're not quite together there. We're trying to get to the planes to actually fly in a coordinated sort of way as well. So it's a good example of the sort of problems you've got. You've got, you know, 6 degrees of freedom flight. You've got, you know, control actuation. You've got a relative state that you're trying to stabilize. So there's actually an error state in here, which is between the two poses that you're trying to stabilize. And then you're asking the question, how can I actually set that up as a control problem? So from Stefan's talk, we saw he talked a little bit about some of the theory and some of the perspective. How do you choose different groups? How do you tackle a problem? One of the things about observers is that once you've done all of that mathematics, an observer, you have full actuation, right? Because it's in your computer, so you can do anything you want to an observer, right? Once you take a real control system, you have actuators, right? And not all control systems have actuators everywhere you want them to. So you have under-actuation, okay? Another thing, ego states and spatial states. So observers for autonomous systems, typically we're thinking about a system, an embedded agent with sensors on board it. So it's moving through the world. It has all of its sensors on board. It has proprioceptive velocity sensors. It has exteroceptive position and bounding sensors. And these sort of sensors have a particular structure, which I call an ego variable, an ego state. So you look at the world from the perspective of the robot. Control problems are often the opposite. They're spatial variables. That is that I have a robot in the world and I want my controller to move the robot in a specific way in the world, okay? And so that means that you have to actually think about this other perspective on variables, and you need to worry about, and that's where this left and right sort of symmetries come in, whereas observers are almost always right-handed symmetries. Some control problems are left-handed. And the other thing is that observers are almost always kinematic systems, right? So we're measuring velocity, because velocity sensors are physical things that we can measure. And so then we're estimating state, configuration state. And so there's no dynamics in there, right? Whereas dynamical systems, they have dynamics. You have to start worrying about the dynamical systems. So there's a bunch of things that are in the control problem that aren't in the observer problem, okay? All right, so what I'm going to tackle today is only one of a bunch of control problems, and it's the one that's closest to the history of what we've done before. So I'm only going to tackle trajectory tracking control. And however, having said that, that is, you know, if you're a roboticist and you do path planning and then you've got a trajectory and then you have to do trajectory tracking, that's actually one of the most powerful frameworks. So the idea will be we'll have some desired trajectory in black. We'll have some actual system trajectory. We'll always assume that we measure all states. We're not going to do any of the estimators here. You put your estimator on yourself and worry about your separation principle, not in this lecture. And the goal is then to build a controller that actually stabilizes the system to the state. All right, I'll do it in 3 parts. I'm going to talk about an SE2 tracking problem and constructive nonlinear control. I'll talk about the equivariant regulator and a reduced attitude tracking problem. So this is an LQR type construction. And then in the last time, I'll talk a little bit about dynamics and Lie-Poisson systems and the symmetries that you can actually put on real dynamical systems. Okay. So left invariant kinematic control systems. So the archetypal control system is this x dot equals xu. Okay, so we've looked at that this morning. And we're going to add to this that the velocity that so this is a kinematic system, right? Not a dynamic system. The velocity u that we're going to deal with here is created by a set of actuators, okay? So I'll put a slide up in a moment for the Robomobile or something. We imagine that we've got high gain on the dynamic part of the system, and so that we're essentially stabilizing a set of velocities, and they go through some basis of inputs in the Lie algebra, okay? So that's the sort of the system that's in the back of it. Let's just turn that into a real system. So on SE2, so this is a car moving on the flat plane. It has an orientation angle theta, has a position x and y, right? So that's the sort of the mathematical model of it. And probably everyone's seen the dynamics of it. It's got a forward velocity u. I think little v is what I use often, but I've used little u there. So it's driving in that direction, has a non-holonomic constraint in the vy direction. Whoa, I didn't know that was a touch screen. Sorry about that. I'll get my hands off that. They've got a touch screen here. That's pretty cool. This campus is bizarre, right? I mean, it's... Yeah, sorry about that. Beautiful, thank you. Good enough. I'll stand back. I'll point at this one. This one's not a touch screen. Got a non-holonomic constraint, so it's under-actuated and fully constrained in the angular velocity, okay? And so here we see the actual structure of the SE2. So this R matrix is a 2x2 rotation, so it's just got one angle in it. We've got a position, x, y, and these input matrices are in the Lie algebra, right? So this is the compact part of the Lie algebra, the SO3. It looks like the skew symmetric, but just for you know, one angle, right? And we've got actuation in the x direction in the Lie algebra and no actuation in the y direction in the Lie algebra, okay? So it's exactly one of those systems, x dot equals xu, okay? So I'm going to choose a desired trajectory that I want to stabilize, and I'm going to require that it's a feasible trajectory, which means that there exists a set of UI and DTs that actually create the trajectory I want. So obviously I don't want to try and track a trajectory where the car is sliding sideways. That's not going to work. Right, nonlinear constructive control. This is the basic formula, right? So for the moment, imagine that this is just a nonlinear system on Rn. This is what a control engineer learns to do. So we've got a feasible desired trajectory. So we define an error. So on Rn, okay, you write down psi minus psi d. Why not? It's what everyone does. So then we compute the error dynamics. So we just take the derivative of this, substitute in. The key thing here is that we've got something in terms of psi and psi d. Don't touch it, Robert. That's... so what we want to do is we want to write this in terms of the, yeah, I won't use that one either. So we want to write that in terms of the error and the exogenous known signal psi d. So basically what that line in the middle does is it takes the E dot, it takes every instance where you get a psi, rewrites it as the error E minus psi d, right? And then it treats psi d and all of the other time variation in UD as a time varying function. So you end up with something that's non-autonomous, but a function of the error E and an input U, okay? So then your standard approach, you take a Lyapunov function, which has a zero, its minimum at E equals 0. You compute the time differential along these dynamics, which are time varying, and then you algebraically choose an input U for every time that makes that decrease. And then you start using Lyapunov and Barbala, and you worry about time variation and uniform continuity and all of those sort of things, right? So that's basically how people do that problem. So let's do that for this particular example. So we're on SE2. So we have our manifold is a Lie group in this case, but I've just written it as an M. And because it's a Lie group, I have available group multiplication and group inverse, and so I use them to construct my error, right? And that's essentially what we did in 2005 when we started doing the filters. We just said, well, we've got an inverse. It's just the algebraic structure of a group, and we use it, and this is almost the only place you use it, right, in that whole construction. So we construct an error, and this is a classical Lie group error, and I've got a slide in a couple of slides that I'll actually talk about different errors. But this is the one that everyone would pick based on, you know, studying robotics in 4th year at a university. And then you do the formula, right? So you take your error, and the goal is to send the error to the identity. That's the origin of your Lie group. And so you compute the error dynamics, and you get exactly what I was saying. At the bottom there, you get an expression which has the error in it, and it has the exogenous UD signal, so it's a time-varying signal coming into it, and then you have your input U that's coming into that as well. So, okay. So let's just think about what this error is. We're all roboticists, so this diagram here makes a lot of sense. So what we've got is we've got the robot that we're actually trying to control, B. We've got the desired trajectory, BD, that's moving through space, and we have some reference frame which actually define the coordinates that we're working with. And what we want is the transformation between BD and B, which is the X. I'm using the Spong notation here, this notation here. And so if we send this to 0, then clearly, you know, BD and B are going to end up identity, right? And we've got coordinates for these guys, so I just, I can rewrite BD in terms of these arrows. So I go backwards down this one and forwards down that one, or the other way around, whichever way. And the zeros cancel, and then I invert this one, and I get back my XD to the -1X, right? So that's what that error is, and that's why it's the classical point. The note here is that it's independent of 0, right? Because that error is defined from the perspective of BD looking at B, right? So it doesn't depend on the frame of reference. However, when you think about doing the control, if you want to actually stabilize this, you've got to get rid of the effect of UD, right? Because UD is actually disturbing the error dynamics. So the obvious thing to do is to cancel UD with U, okay, where this adjoint E is because the error was, one was left and one was right, and then you get to do what you want with the delta, okay? But that doesn't work because you're not fully actuated, okay? So I've written this error out here, adjoint E to the minus 1 of UD. So UD is something that looks like this. That one, by the way, is a typo. That should be a 0. But this is your desired angular velocity. This is your desired linear velocity, right? And I wrote out the actual errors. So basically, this is the rotation part of the error in E, and this is the translation part of the error. And you can write those out in terms of the desired things. So then I've just done matrix multiplication there, and what you can see is that there's a skew-symmetric matrix here which you can completely actuate, but then this guy here is it's a 2 vector, right? So it's got an x component, a y component. You can cancel the x component, but you can't cancel the y component, right? So the E2 component of that vector, you can't cancel because it's underactuated, right? So what it is, it's telling you that the error has components in the non-holonomic direction of your vehicle, right? The error decreases in a direction that you can't actuate, okay? So you can't tackle that, right? So the error might be increasing in the directions you can actuate, decreasing in the error that you can't actuate. So if you could actuate it, you'd go downhill in that way and you'd be fine, but you can't actuate it, and so you can get yourself into strife, right? Never turns up in observers because you always have full actuation in delta, right? But it does turn up in controllers. And this term here is like the drift dynamics of the error, and basically when you try and control things, then you have to dominate that, right? And there's a number of controllers that have done that. And this has been studied in the literature, of course, in the 1990s when people were doing non-holonomic vehicles. This was studied to death in period. All right, so from our perspective, then let's look at this error. This is the right invariant error. So what I've done there is I've swapped, instead of xd to the minus 1x, I've written xd to the minus 1, right? And this is the error that actually Stefan would have written down. This is the one that comes out of the equivariant theory. And you can see what it does for you, right? You take the derivative of this error and you crank through the mathematics, same mathematics as what we did before. What you end up with is that the UD and the U turn up in the same space, right? So they actually, in that error, they turn up in the same algebra. Now, UD is only actuated, because it's feasible, is only actuated in the 2 actionable directions, which means that you can use U to cancel UD, okay, in this case. And then you've got some actuated directions that you can do your actual control with, all right? In particular, if I choose U equals to UD, I get what I call synchrony, which means that the error is constant. So you can take that, and I won't go through the actual control design, but you can define a Lyapunov function, and now your Lyapunov function has no drift term, so you just take the gradient, project the gradient onto the actuated directions, put a negative onto the actuated directions, you get something that's always decreasing, and you get a control algorithm that works. And so what we've got here is just a simulation of our algorithm, which I think is in the blue, and the other standard algorithms, a bunch of them from the literature, which shows similar sort of convergence. To be honest, because in nonlinear control, when you do this sort of control, you impose a certain decrease rate on the Lyapunov function. You typically don't see much difference in the actual rate of convergence of the different algorithms. What you do see is a difference in the actuation that you have to undertake to achieve what you're doing, and I'll talk about that later. So it certainly works. Right. An interesting thing to do then is to ask the question, well, what are we achieving by doing this, right? So what's actually going on? So in particular, we use this right invariant error. And the right invariant error is an interesting construction, right? So we'll go back to our robotics and we'll think about, well, what does this mean? I'll start with the right invariant error, xd to the minus 1. And then the next line there, I'm just writing them down in terms of the standard Spong sort of notation. So you know, X is the transformation from 0 to B. So 0 in the top left, B on the bottom right. I just write them down, write them out, and you get this line 3, which doesn't make sense, right? So if you've done Spong's book, right, you know that when you take a rigid body transformation and another one, and their top left and their bottom right frames don't match, it doesn't mean anything, right? So this is why nobody did this for years and years, okay? So what's actually going on, right? So what we do is we pre-multiply by the 0 BD, well, by identity, right? And then I've got this term here, which is when I invert that term, I get BD 0. That contracts with 0B, so I get this term in the middle, which is my left invariant error. And then I've got these two transformations around the outside, okay? Now, this transformation here can be thought of as a coordinate transformation. So what it does, if I take something in frame 0, expressed in frame 0, apply this, I get something expressed in frame BD. This becomes a transformation. It takes BD to BD. Well, it's taking BD to B in BD, and this undoes the coordinates of what's going on, okay? So that's what the right invariant error is doing. And so that's what I've drawn here. It's taking the frame BD to B, but from the perspective of 0. Now, the problem is normally when people do robotics books, you think about the frame of reference, you think about the pose, another frame, and we write down the homogeneous coordinates of the pose, right? Now, that's the first interpretation of Spong, right? That's just coordinates. There's another interpretation, which is that I can move from this position to that position using exactly the same homogeneous transformation. That's the rigid body transformation aspect of it. The third one is then if I have a point in space, the coordinates of that point in the body frame become the coordinates in this frame by applying it, right? I'm interested in this second one, the actual rigid body transformation. That's actually the physical transformation in space, right? So that interpretation is exactly correct, but our understanding of it is locked into the idea that you're always in the frame of reference that you start in and moving to another frame. What we're doing here is we're generalizing that to being my reference frame is here, I start with that frame there and I move it to here. So of course, when I move to here, I move the whole space along with me. And that's really the change of perspective that's going on with this error. That's what's going on. Why is it important? When you try and define an error on a moving object, so when you define your error with respect to the moving base, of course, as the base moves, you get changes in the error, which makes things hard to compute. And that's actually where the drift term comes from. When you're stationary and you're looking at it moving, you get this invariance to the movement. And so in the correct geometry, you get this very nice expression of how to actually understand the error changing with time. And you get this, what we call synchrony. So that's sort of a nice geometric understanding of what we're actually getting out of this. So let's just look at what they look like, right? Because this is really useful. Yep. Yep.
Slide 17, show that the error dot is 0.
Yes.
Yeah.
Slide 16, yes.
It's not 0. And then on the next slide, it shows that the active reactive conversion.
Yeah, okay. So I'm jumping over. So this is the synchrony part of it, right? But the controller here, U, is just cancelling the predefined motion. Then on top of that, you add a correction term. Okay, so when you design a controller, you have first to instantiate the model. So you have to, it's like a model, internal model. So if I want to do trajectory tracking, I input the velocity that would keep me exactly on the trajectory I want. And then I look at, and then I'm tracking along next to where I want to be, and then I adjust the correction. Yep.
System error, or it's just part of the
No, this, for this very simple system, there's really only 3 states. So this error is everything, right? It's rotation, position, and both X position and Y position.
the Lyapunov function will converge to a constant value, non-zero value instead of.
If the error, if you've got a Lyapunov function of E and E dot is 0, then the Lyapunov function is constant, doesn't change. Yeah, that's because actually, I forgot to say, so the actual control I put in is UD plus a correction term. That's what I actually do, right? Yeah, so I apologize for that. Yeah. Okay. All right, so let's just look at those transformations. So on the left, we have the body transformation, right? So I've got BD going to B. So when you apply, when I apply a rigid body transformation in my own frame of reference, I rotate, okay? So you can see the rotation to vertical, and then I translate, okay? When I apply that same transformation around a reference frame, right? I do the same thing. I rotate, BD rotates, but it rotates around the axis, okay? And then I translate. And that translation you can see is exactly the same as this translation. It's just been moved through space in a different way, okay? Now, what's cool is when you actually then move. So both of these vehicles have now moved exactly the same way. So this one has gone forward, turned right. This one's gone forward and turned right, okay? So the actual vehicles have the same identical motion. So this is E dot, basically. And then I can compute the error from here, right? So I rotate and I translate. So I rotate the right amount, but the yellow translation's not the same as this red translation, right? So the old ET0 in the new frame is drawn at the top there. The yellow is where you went to before, okay? But this is the right invariant error, right? And so you can see this is what we just saw before. You rotate and translate. I move, okay? And now magically, I rotate and translate, and you end up in exactly the position where it's gone to. So that's graphically showing you that property that if you pick this error in this particular way, it preserves the transformation. It's really useful because, you know, conceptually, mathematically, you write down the error and you go, oh, that's honky-dory, right? That's going to work, right? But then conceptually, you're not changing anything. The robot's going exactly the same place, right? What's happening is that your error is changing its sensitivity. So in fact, it's possible with the the right invariant error where you have XD transpose, XD transpose, if your XD trajectory goes to infinity in a really bad way, it's possible for you not to converge, but for the error to converge, right? Because of conditioning, basically because you end up, you know, computing everything around this reference frame and you get a long, long way away. And so then a tiny rotation does a lot of translation. And so you end up minimizing the translation and the position can diverge, okay? Diverges linearly. So you have to be really careful about compactness of the trajectory tracking and such like, okay? How am I going? All right, let me talk a little bit about homogeneous symmetries in the equivariant regulator. So what I wanted to do in this one is break the mold a little bit that every problem is posed on a Lie group, okay? So this problem is not posed on a Lie group, it's posed on a homogeneous space, which means that the Lie group is a separate object acting on a lower dimensional manifold. So that's the goal of what I'm trying to do here, and then I've wrapped in a little bit around the equivariant regulator. So this is the control problem that we're considering here, and we call it the reduced attitude dynamics problem. So the idea is we've got a quadrotor, and we want to go somewhere with the quadrotor, but we don't actually care about the orientation of the quadrotor. So the actual control problem is that we want the thrust vector eta of the quadrotor to point in a certain direction. We want the position of the quadrotor to be somewhere. We want the velocity of the quadrotor to be something, but we don't care about the yaw. So it can fly around, it could be spinning, whatever it wants, right? So as a consequence, we don't actually have a Lie group here. So Jake this morning was saying, you know, the sphere is not a Lie group, right? So this is a homogeneous space. Obviously, the symmetry on a homogeneous space is going to be SO3. So I'm going to introduce the dynamics here. So these are just, I mean, these are basically, we've just pulled the dynamics out. So this is the kinematics around eta. So this problem actually was done by James, pretty much, the way we're setting it up, because we're setting it up on SE23. So he did this. I think you did it for the full rotation, didn't you? Yeah. So you missed out on just my tiny little contribution is to make it an eta rather than a rotation matrix. Anyway, and so what I'm going to do here is I'm also going to add what I call a virtual input W in here, and I'll show you why that has to go in later. But I'm going to set that W to 0. So in Stefan's talk, he mentioned at one point that, oh, there's some additional states that got added in. That then, but he didn't elaborate on it. This is one of those sort of situations where to get the geometry, we're adding in an additional state, but we'll always set it to 0 in the actual algorithm. And I'll show you how that works in a moment. All right, so the first thing is this left-right, okay? Left and right. So this problem is a spatial variable. So when I say eta and I want it to point in a certain direction, you can see what's going on. I've got a reference frame on the ground and I've got an eta direction. This eta is written in spatial coordinates and it's the direction that I want to go as an observer sitting on the reference frame looking at the vehicle moving, right? Most observers aren't like that, okay? So in fact, the classic attitude observer, measures a gravitational direction or a magnetometer or something like that, measures it in the body frame and is studying it in the body frame, right? And so in that case, you're actually writing the coordinates of the gravity direction in the body frame, right? So these sort of variables I call spatial variables, and they typically have left-handed symmetries that make everything work. These sort of variables are ego variables, and they typically have right-handed symmetries, and you can see the R transpose E3, which is a right-handed symmetry that Jake was talking about earlier, okay? And so when you study equivariant systems and you look at the observer literature, almost everything's written down in right-handed symmetries. So all of my work is written down in right-handed symmetries. I sort of have really composed it over the years to try and get the community to go that direction. When you start doing control problems, okay, you're dealing with spatial states, you have to use left-handed symmetries to get things to work. So this is a symmetry that I'm going to use. I'm going to use just a rotational symmetry, SO3 on eta. I'm going to use rotation. This is the semi-direct type property that's going on here. So this is an SE23 symmetry essentially that I'm using here with just the rotation acting on the direction. So then the velocity is a semi-direct product, the position is a semi-direct product. So, I mean, some of this maths is going to start going a bit loopy, right? But what we're going for here is the conceptual construction. I need to put a symmetry on the input space, right? Because I'm looking at equivariance. So it makes sense that the input omega transforms with the rotation. The acceleration is a scalar, so it doesn't transform at all. That's just a scalar direction there. The gravity direction does transform because of the way it works. And then this is the input, the virtual input. And really the reason that's there is because in order to get this symmetry, the V plus Vx, I need to use the virtual symmetry in the position. So there's a little bit of stuff in the background there which I don't have time to talk in detail, but I'm happy to talk to some other people about later on. So this is a lift, right? So we're studying this as an equivariant system, and we can actually write down the lift. So this lambda that Stefan was talking about, it has a skew symmetric part in the top left, has this combined part here that basically gives you your V dot dynamics, and it has this bit here which basically gives you your P dot dynamics, right? And so you can sort of see what's going on there. And so the lifted system has this structure at the bottom here. I mean, maybe I'll move that out of the way there. It has, for those of you that have looked in the area, this is actually a drift term, xn minus nx, that reproduces the P dot equals V bit of the equation, right? So again, I didn't write that down, but there's a bunch of papers about that. And then we have our bit, which is the inputs, which is lambda times x. And I said it was a spatial problem, so it's going to be a spatial velocity that I'm modeling, right? So it's lambda sits on the left of x, right? So if it was x lambda, it'd be a body type problem. Lambda x, it's a spatial type problem, okay? And this is the property that Stefan was talking about, right? So those dynamics on the group, right, correspond when you project them down through the group action. to the actual dynamics of the system that you're interested in, right? But remember that the group is actually higher dimensional than the base space, okay? So what we want to do is we want to do trajectory tracking, and this is the interesting part here. So we have a trajectory, eta d, vd, pd, with inputs ud, omega d, ad, omega d, and so that's a feasible trajectory, right? But it's actually really hard to formulate an error between the trajectory on the actual manifold and the system on the actual manifold. That's actually a really hard problem to formulate an error on that. So what we do is we lift the trajectory to the group, right? So this system here, xd, evolves on the group, right? And has this property that when I project xd of t through the group action down onto space, I get the trajectory I want, right? But it's in a different space, right? And so in particular, this has more dimensions to it than these. So we sort of, we hypothesize, or we synthesize additional degrees of freedom that don't change this property, but give us this high level structure. And you can do it very easily, right? By picking the initial conditions correctly, and then you just solve this ordinary differential equation for those inputs, and it'll do the job, right? So generating that capital XD trajectory is quite easy once you've got the psi D trajectory and all of the symmetry. No, it isn't. You can do stuff in the stabilizer. Yep, so you can go up and down in the stabilizer like you want.
Also, Rob.
Yep.
So previously, like, it's all about picking the action, but when we look at equivariance, there's also like a psi. So where's the psi show up in this?
It's in here. So we had the psi here, which makes this an equivariant lift, and without that, you don't get this property here, right? So it's sort of hidden in the maths, but it is there, and it's really important. Yep. Yep.
Maybe it's obvious if you have worked in this topic, but why do we choose the particular symmetry here that it shows? Like, why do we want this SE2?
Yeah, why have I chosen that symmetry? So it's not a dumb question. It's a really profound question. So what you're actually asking is, given a certain system, what is the correct symmetry to use to answer that? I don't know the answer to that, right?
But for this particular problem, does it make sense? Why do we want this particular?
So I used this symmetry and it worked. I could probably give you some other answers, but to a certain extent, that's where we are in the theory, right? Certainly in control. In state estimation, we've got at least just come out this Automatica paper where we used 6 different symmetries and did extensive simulations and compared them, and we can sort of say, well, we're pretty confident that these symmetries are better than those symmetries because we get better results. But I don't have like I can't stand here like Lagrange and say, oh, that's because blah, 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 right? So to be honest, it's just case by case academic picking the symmetry. Yep. So
the analogy is how do you pick a Lyapunov function candidate?
Yeah.
Yeah. Like if you're in the same realm of, oh, there's some intuition because of energy or this, that, or the other. But we all know if you choose the Lyapunov function candidate, you're going to get different properties, right? Well, it's the same thing with picking the action.
But for Lyapunov, you have some intuition, like you think about energy. Or
yeah. So we've got some intuition about this. SO3 is a pretty good action on S2, and we want to couple the velocity in with the SE2-3 because we know that actually picks up the structural. So there's that intuition is there once you work in the field, but. Yeah, that actual high level, is this the right symmetry? And what would be the metrics to measure a symmetry against another symmetry? We actually don't have.
Yeah, so follow on that too. So that paper that they just mentioned, this Automatica paper, like they went through these 6 different ones. And really it boils down to, you got to look at every single Jacobian, you figure out just how picking that symmetry impacts the downstream Jacobian, which then is going to lead to different convergence properties. Like it's, like from my perspective, this is another tool to figure out what is the best way to get Jacobians that are going to lead to the state dependence, which will lead to the best convergence.
Yep, in observer theory, it's about linearization error. Yep.
Yeah, that's observer theory.
Yep.
I was just going to say, my intuition is you pick the symmetry that makes the aerodynamics look the most linear.
Yep. Yep. That's exactly the same answer. Basically, you pick a symmetry that minimizes linearization error. And that's a little bit problem dependent because in some problems, trajectories particularly emphasize certain parts of the state space, errors in certain parts and other. That's why what Stefan was saying. Yep. Okay. We really are getting close to cutting edge in these talks when we get there. All right. So, right. So the point is that we construct exactly the same error that Stefan was talking about, right? This E. And it has the property that you would expect, right? So if I take psi d, right, it's constructed as a prediction of psi 0. But if E equals psi 0, I substitute it in, but E is defined as we see above, and so I get a psi d minus 1, I get back psi. So even though psi d, xd, the big trajectory has additional degrees of freedom in it, right, that are doing weird stuff in the stabilizer, if the error goes to the desired point, then your trajectory is going to be correct, right? So the fact we've got extra degrees of freedom in the desired trajectory doesn't affect the underlying tracking control, okay? And I have this comment here, which is an interesting comment, right? Which sort of tackles some of these problems. So when we do this lift, right, this is all about actually picking the lift, the lambda. The reason we've done the particular choices we did was to get this property that Stefan mentioned, right, which is equivariance of the lambda, right? I won't talk about how that all ties in, but it's basically the fundamental structure that's letting us get nice properties in what we're doing. The interesting thing to say here is if we do this way, this is actually very different from what you would get if you went and read Marsden's book or Bullo's book and did mechanical connections. A mechanical connection is essentially a way of picking a lift in their structured space, but it doesn't have this property, right? So the mechanical connections change things around in another way. So that's just another perspective of what's going on. Yep.
Like you can think about like a reductive decomposition as a
Sure. If you have a reductive Lie group, you can do both the same.
generally.
Yeah, in general, if it's only if you've got a reductive group that you can do that, and that means that the stabilizer is compact. Yep.
And when you said like things can happen in the stabilizer, but it doesn't affect the control.
Yep.
You mean asymptotically, like because of this analysis?
No, actually, in the stabilizer, it doesn't affect instantaneously, right? So stuff can happen in XD, but the actual trajectories should be fine.
Can you say like, regardless of which lift you pick, the control action is the same instantaneously, or only like asymptotically?
I might take that one on notice and have a think about it. I mean, my intuition is it doesn't make a difference, but I better check. What it potentially does is internally rotate some of the control surfaces or something, right? So I have to think about that. Yep. Like, I mean, on the quadrotor, you're rotating the quadrotor. So different motors are going to have to act to do the same motion, but you know, okay, you have actuation in all those degrees, but it might affect a little bit how the control is realized, right? That would be my intuition. Yep. Okay. All right, so now I'm just going to skip through a couple of slides really quickly so I can get on to the rest of the talk, but in these error coordinates, you do a linearization, okay? And, you know, the input matrix now you have to worry about, so you linearize, and you can see that this group action on the input space actually gets linearized as well, so you have to worry about that. I won't spend long talking about this, but the underlying kinematics pulls out separately from the other part of what you're doing. And if you want to do the EQR, then you propose a cost function. You've got the linear model underlying the error, so you can run your Riccardi equation. You can pull out the adaptation term U tilde, and you can feed that back up into the controller, and you get something that works, right? So once you get through all of that modeling, it's really just LQR in local coordinates, okay? And it works quite well. So we applied the best that we could find, a projected LQR algorithm. It's essentially solving the LQR on the SO3 and then projecting it down onto the translation. And then we did it with the geometry, and we got, you know, particularly it's this bottom right graph is probably the one that's, I'll point to this one because everyone can see it. So this is RMSE error of the trajectory, and this is our goal point up the top here on SO3. And what you can see is that for the PLQR, when you're far from your desired point, you're getting quite a lot of error, okay? And so the good geometry is doing a much better job far away from your desired trajectory, but a very, very similar job once you've converged, okay? And that's typical, very typical of equivariant systems. They're good at getting you large domains of stability. 10 minutes for the whole of dynamical systems, Lie Poisson systems. All right, strap in, strap in. All right. Consider a mechanical system on a Lie group. So we're only going to deal with systems on Lie groups at this point, right? Okay. And I'm going to, this is from, you know, the classic approach, we're going to consider an invariant system. So what that means is that the natural left action on the Lie group, so the x and xv action on the Lie group, on the Lagrangian, the Lagrange is invariant to it. So, right, this LIV is the same thing as L moved to x, xv. So, you know, if you just left translate things on the Lagrangian, doesn't change your kinetic energy, right? So this is bog standard, almost all physical systems, where you are in the world doesn't matter to what your kinetic energy is, right? So if I'm in one place with a certain velocity, I move to another place with the same velocity, same kinetic energy, right? Doesn't depend on where you are. And I'm just considering kinetic energy at the moment in this talk. So the Euler-Lagrange equations work with the Lagrangian, of course. The Hamiltonian equations, or the Hamiltonian perspective, works with momentum. So we define a momentum, which is the differential of the left trivialized Lagrangian. So this is a left trivialized momentum. So this P lives in the co-algebra of the Lie group. So that's basically row vectors as compared to normal vectors of a linear space. And the Lie Poisson system that's associated with that has a set of kinematics, which is your standard left invariant kinematics. I'm happy to share the slides, Costas, you don't have to write everything down. And the standard Lie Poisson equation, which has the bracket here. And don't forget the physics, right? Because actually, in order that this makes physical sense, the momentum and the velocity have to be connected through the differential of the Lagrangian, okay? All right, so let's just think about SO3, because they're scary equations the first time you see them, and they're really not scary at all. So right at the top there, I'm talking about elements of SO3 Lie algebra. So they're these skew symmetric matrices, and I'm using this little cross operator to go from a vector to a matrix, which I think a lot of people have been used to. And so this inner product, so I've got a covector P, which acts on linear vectors. So these two things contract together, and I'm just going to write it as a trace of P transpose omega, which is the same thing as P transpose, the little P transpose little omega, okay? And so that's a covector acting on a velocity, okay? So the left trivialized Lagrangian is nothing different from just the angular momentum and acted on by angular by velocity. Left trivialized momenta is nothing different than just the inertia times the angular velocity. And the kinematics and dynamics look like this. So the kinematics, I think we saw already in Jake's talk. So dynamics, this is the dynamic equation that was there. So adjoint, the adjoint. I've never done that before. So anyway, the start adjoint in the velocity direction acting on the momentum. And what's really going on there, we've got this relationship down here, which is sort of nice, that when you do this start adjoint, it's like doing a bracket, like the little adjoint is brackets. But because it's starred, you've got a transpose. And so then that's a skew symmetric, so you get a minus, and then bracket is the same thing as omega cross P with a cross. And so when I put that in up the top here, you just get the standard equations for angular momentum that we've all seen in our underlying thing. So these guys here, I've got another slide later on where I go through some of the maths how to work with them. They're not actually scary once you get used to them, right? But they're terribly scary when you first see them, right? I remember I used to not read papers with any adjoint star in it. That was one of my rules when I was an undergraduate, when I was a postgraduate, sorry, when I was a PhD student. All right, this is a trick now. So what I'm going to do is I'm going to discard the physics. I'm throwing away the fact that P equals dLV, okay? I'm going to study what I call an extended Lee-Poisson system. And this is not a physical system anymore, right? I can choose any velocity I want. My momentum will evolve in some weird way because my system will be going sideways. My momentum says I should be going that way. My system can go anywhere it wants, okay? But what I'm doing is I'm getting access to the actual geometry of the underlying problem this way, okay? So if I solve the problem for the extended system with arbitrary free inputs V and tau, okay, it's a control problem. So if I can study the problem from that perspective, and then when I design my controller, I choose V equals I to the minus 1p, what I'm doing is I'm instantiating the correct physics, and then whatever the tau is that solved the problem will actually solve the whole problem, okay? So I can study the problem, the geometry of the problem for free inputs, but I have to remember that in my control, I have to apply this, okay? So this is a different perspective on what we're doing. So then I'm going to throw a group at you, right? So this is a group. It's been around since the 1960s. I think I found a reference. Brockett certainly knew about it. But it wasn't useful at the time, right? That wasn't the invariance that they were doing, because this is a transitive group action on the cotangent bundle of the underlying space. So the group, we call it this sort of extended lifted group up the top here. It's a semi-direct product, and that's exactly the group action there. So you can see the first part, which is a copy of the group. So this is a configuration, Q1 and Q2 are configuration type objects. That just works normally. But the momentum, remember momentum's a linear space, cotangent space, so you expect additions. But I don't just add them together, I apply this starred adjoint of Q2 to P1 and add it together, right? And that's actually a left multiplication, it's well defined. The reason why the star normally swaps the order of multiplication, but the fact that I'm doing it to a Q2, which is a right multiplication in the Lie group, means that I've got right equals left, if that makes sense. Don't worry if it doesn't make sense. All right, I also have a group action on the inputs, the psi down here. So I have, well, my inputs are V and tau, and then I have two group actions. So the first group action really is just the group multiplication, right? Because this is a free action that I'm doing, right? My group has the same, I mean, it's not the same state space, right? Because my group is this group that I've just done. My state space is just G direct product with the co-algebra, okay? So the state space is not a group, but the group acts on that state space, right? And so there's a free action, and then the input action, which really you have to read the paper to understand. So I won't go there. But there's a key point that if you apply this action, so if I have my system and it's doing something here, and then I apply this action to transform into another place with another momentum, I've broken the physical structure of the system, right? So you can't keep that DLP property and do this, ooly dooly. So I should have a quick think about dropping some material out, but I'll quickly. So I'm going to stop 2 seconds and talk to my co-organizers. What should I do? I've probably got 5 or 10 minutes. What do you want me to do?
5 minutes of lunch break, no problem, I think. So
Is everyone happy if I sort of finish? I'll try not to go too fast. 5. I'll try for 5. I'll try for 5. Okay. All right. So this slide here is, I won't do the second half of the slide. I'll do the first half. Basically what I'm doing is I'm trying to make it less scary, right? So all I'm doing here is at the top, I'm just writing down what it means to do a star, right? So what it means to do a star is I've got an add Q star and it acts on a co-algebra element. So we don't know what that means at the moment, but it makes another co-algebra element, so I can certainly contract it with a velocity, okay? So that's the top left. And then what star means is it's the same thing as if you contract P with add Q on V. Oh, I do know what add Q on V is, right? That's my adjoint operator, okay? So that's what add star actually means, okay? So let's just do a calculation with it. So I'm interested on SO3 in computing add star Q of P acting on an angular velocity omega. So I move the add across, that's the first thing I do. Then I have the contraction, which I know what the contraction is, right? Then if you think about it, add Q of omega is just Q omega, right? And P transpose, and that's pulling out the cross element. So I just get this equation. And then I think of this equation, I just pull a Q onto the left, so I get a Q transpose P transpose omega. And then I go back over here and I say, okay, well, that's got to map back to here. And so I get what add star QP is, right? So in fact, almost all of these problems are actually a carbon copy of that, right? So it really looks like transpose the group element and pull it back through this, whatever the cross is. It'll be a wedge in a general group, right? And this is the little add star operator, and I'll leave you to read that. But it really is, it's not hard stuff, right? It's really scary at first, but it's not hard. All right, so this is one of the important results that we got. If you build this symmetry in this way, right, and remember we had to forget about the physics to do it, right, which is a sort of a weird thing to do. Suddenly you get that the Lie-Poisson system is a left invariant system, right? So in fact, at the end of the day, what I'm going to write down is the Lie-Poisson system is just x dot equals xu, where u is v and tau, right? And so I've got the proof here really quickly. It's useful just to take a moment to go through it. So x is xq, xp, so the q part and the p part. Z is zq, zp, the q part and the p part. And so left multiplication of z, right? The first part is the direct product, xq, zq. The second part was this weirdo sort of direct product thing that I had, okay? And then I want to take the derivative of Lx, taking it with respect to z, so I'm differentiating the z bit, evaluating the identity in the direction u, and u is v tau, okay? So let's do the first term, xq, zq, so this term here, right? First I differentiate it with respect to the first bit, zq, and evaluate it in v. Then I differentiate it with respect to zp and evaluate it in tau, okay? And the next one's the same. I take this expression, differentiate with zq, evaluate with respect to v, zp, evaluate with respect to tau. So it's a big complicated experiment, but it's just chain rule, right? And let's look at it, right? So dzq, xq, zq is just xqv, right? When I differentiate xq, I just get v. And then let's differentiate this one. So the only tricky one is differentiating the big add. Well, when you differentiate big add, you get a little add, okay? Take my word for it if you haven't seen that before. So you just get little add star v, because zq gets replaced by the v. This term here doesn't depend on little zq, so it goes to 0. So that gives you that term. And then over here, zp, you just get tau, right? You look at this equation, and it's just exactly equal to the Lie-Poisson system. So this is dl xu, and this is the Lie-Poisson. So we've got this really cool situation where I'm trying to do a controller for Lie-Poisson system, and it's just left invariant, right? Well, I just did left invariant earlier. So crank the handle, take the derivative, u minus ud, so those two cancel, okay? And pull them out at the end. Okay, that all sounded great, except you can't do it, right? Because you can't just choose u equal to ud, because when I do my controller, I've got to have v equals I to the minus 1p. Otherwise, I won't be building a real system, right? It's not physical, okay? All right, so that's a little bit tricky. So, however, E dot equals EU tilde is a left invariant system on this particular group. It's a Lie-Poisson system, okay? So I write it down as a Lie-Poisson system with these new variables, a V tilde variable and a P tilde variable that come from my E, and a U tilde variable that comes from up there, okay? So that system turns out not only to be Lie-Poisson, extended Lie-Poisson, but turns out to be actually a Lie-Poisson system with a time-varying inertia associated with the desired trajectory, okay? So I'll give you a reference to the paper. So then you've got this relationship that P tilde is actually I tilde V tilde, and now it's a stabilization problem for a time-varying Lie-Poisson system, okay? So all we need to do is be able to stabilize a Lee Poisson system, dynamical system, and worry about the time varying. So really quickly, just to see how you're going to do that, you're going to use a kinetic energy. I mean, eventually you'll use some energy shaping and some bits and pieces as well. But let's look at the derivative of the kinetic energy. So you're going to get a P tilde dot derivative. You also have a time varying inertia, so you have to worry about the derivative of the time varying inertia. Forget about that for the moment. The P dot derivative has an adjoint star U P tilde, and then the I to the minus 1 P tilde here, and the tau tilde I to the minus 1 P tilde. Now, I to the minus 1 P tilde is V tilde, adjoint star U tilde, sorry, U tilde, adjoint star U tilde P tilde U tilde. Well, that's the same thing as P tilde adjoint U tilde U tilde. Well, adjoint U tilde U tilde is 0. So this is Coriolis passivity coming through, right? So this is what you would expect in any mechanical system, that you're going to get a passivity to these virtual forces, right? And you see it here in the aerodynamics, right? Which is really cool. Then you get your energy, right? This is just the energy, and then you get the time variation of the inertia, right? And the time variation of the inertia is an open problem, how to handle that, right? So we're still working on that. If you have enough actuation here, of course, you can just cancel it. And so we have done that. We applied that, and we've compared it to standard algorithms in the literature. And as I said earlier, when you do this, because these are constructive nonlinear type control designs, you don't actually get much change in the response of the trajectory, right? Because, you know, you reduce the Lyapunov, you know, you design the controller so that L dot is equal to minus L, right? So you get the same transient response. What you do get here is massively less control action. So this top right one, the lower curve there is what our control action is. The top one is the standard industry control action. And so you save a lot because you're not pushing Coriolis forces around. And that's basically what you gain out of doing this. And another really cool thing is that it doesn't rely on any sort of underlying decomposition of the state space. So we've applied this to underwater robots, where you get added mass effects and where the inertia matrix couples linear and angular velocities. And that actually breaks a lot of the existing literature schemes, because they rely on doing a bit of attitude, you know, they rely on doing attitude separately from linear and then cascading. This algorithm just goes over the top of all of that. Right, so studying control problems using equivariant systems, it's actually quite new, right? So geometric control is really old. Control problems are really only being studied in the last sort of 5 years, although I should mention McClamrock's work and Lee's work from the 2008, 2010, I think it was, that they did that work. That's all basically very, very similar to this. It's all working on that. Equivariance helps with controlling underactuated systems. Defining a lifted target trajectory on the symmetry group allows for global tracking and improves LQR, and the Lee Poisson actually also, those dynamical systems have a symmetry for them as well that we know about now. So thank you very much.